Hi, I'm Sarah. Longtime viewers of the channel might recognize this number 5 crossbar trouble recorder. It's the main way that the telephone switch communicates with maintenance staff, and in previous videos we got it running again and did some further repairs to replace a few broken punches. It's been happily punching cards for us since then, but there's still a lingering problem. We're running out of blank cards. This is one of the correct cards for the machine. And this is one of the incorrect cards. They look similar, right? Well, they are the exact same size and shape, but everything printed on them is different. So the holes will always get punched in the same places, but with this card, the actual designations on each position are incorrect. This is a big problem because this machine drops a lot of cards. And when you're actively troubleshooting, you could easily punch 30 to 60 of them in a day. We only have about 4,000 of the correct type left, which might sound like a lot, but that would last us only a few years at the current rate, if that. We've got some ideas for producing new cards, but it's not quite that easy. Back in the day, IBM made the cards for AT&T, and they made them to extremely precise standards. If the card is even a tiny bit too thick or thin, or not cut perfectly, it'll jam in the punch. But it turns out that there's another way to get trouble record data from the machine, and that's what I want to tell you about today. Before we dive right into the cool thing, though, let's first take a moment to review what trouble records are and how they're produced. Bell Labs developed the technology for the trouble recorder for the very first number 5 crossbar in 1948. Earlier switches, like the panel and the number 1 crossbar, had diagnostic output in the form of lamps that illuminated to display the state of the machine at the moment of a failure. But the problem with the lamps was that they could only display one failure at a time. And if there were subsequent issues after an initial lamp display, that data would be lost if the lamps weren't promptly observed, written down, and then cleared by a technician. These lamp panels use relays as memory and are only able to buffer one display at a time. To solve this problem in the number 5 crossbar, Bell Labs designed the trouble recorder, which punched the necessary information onto paper cards and then deposited them into a bin where they could be sorted and analyzed by the maintenance staff when convenient. The data on the card is actually a core dump of the machine's state at the exact moment that a call failed to complete. Using that state, we can piece together exactly what the machine was doing and then recreate the failed call using this test panel here. We can then repeat the test as many times as necessary in order to actually locate and resolve the problem. In addition to recording errors, the trouble recorder is also the primary output for the test frame itself. If I want to interrogate the machine and ask it how it feels about something, it drops a card to tell me. And I've actually heard from old switchmen that sometimes if the switch was really misbehaving, they just placed a trash can under the trouble recorder and just let the cards fall straight into the garbage. I don't know how true that is because it was possible to temporarily disable the trouble recorder if you really wanted to, but I've heard this story from multiple people, so in theory, it could actually be true. The interesting question here is, how does the state information get from the switch itself into the trouble recorder to be punched on a card? Well, the switch is controlled by a few giant CPU-like relay circuits called markers. And when a marker detects an error condition, it halts itself and bids for access to the trouble recorder. If the recorder is available, the marker connects to it through one of these columns of relays in this frame, the master test connector. Each relay has 30 contacts. All of the relays in the column operate at once, and there are 36 of them for each marker. So in total, 1,080 wires are connected from the marker and the rest of the switch through these relays. Each contact on each relay represents one Boolean value, either a ground or an absence of ground. Ground causes a hole to be punched in the card, and the absence of ground causes no hole to be punched. But the trouble recorder doesn't have 1080 hole punches inside of it. It actually only has 120. So this giant data set needs to be fed into the trouble recorder in chunks of 120 bits at a time. And that's what these relays do here. The recorder begins by moving the card into position. When it's ready to punch the first set of holes, it causes this set of scanning relays to operate. Each set of 4 scanning relays funnels 120 leads at a time into the trouble recorder. And each lead that is grounded will cause the punch magnet inside the recorder to operate. Once those 120 holes have been processed, the trouble recorder moves the card one row forward into the next position. At the same time, it operates the next set of scanning relays, which funnels the next set of 120 leads to the punch magnets in the recorder. The card needs to be advanced a total of 9 times to allow every row on the card to pass under the punch magnets. After the last row has been punched and the final set of scanning relays has operated, the card is ejected from the machine and the marker is then released to handle another call. Here, we can see the scanning relays operate in slow motion. Each set of these is buffering in a subset of the total data to the recorder. And here, we can see the recorder punching holes in the card. Only 60 magnets are visible here, but there's another 60 on the back of the machine. This entire process takes about 1 second. The marker halts, the state is buffered into the columns of the connector relays, and that data is fed into the trouble recorder 120 bits at a time until the entire card is punched. Now, by the 1970s, computerized electronic switching was taking over. But these old number 5 crossbar offices couldn't just be replaced all at once. So their electromechanical trouble recorders were upgraded with what the phone company called automatic trouble analysis, or ATA. This was a system where the trouble records were diverted away from the mechanical recorders and instead sent via modem to a PDP-11 minicomputer in a central location. Then, maintenance staff could be dispatched as necessary to resolve faults, and they no longer had to manually read the trouble cards each day or even physically be in the building to learn about problems. The key piece of technology that made this possible was the MDT, or Maintenance Data Transmitter. It consists of 2 main parts: an early microcontroller called a Procon, and this thing here called the scanner distributor. The Procon is the brains of the operation. In its ROM is a program that makes it behave electrically like a mechanical trouble recorder. Using the scanner distributor, it presents an interface to the 5 crossbar that appears identical to the trouble recorder, but instead of punching a card, it stores the data in RAM and forwards it to the PDP-11 over a 300 baud modem. The scanner distributor is basically a logic level shifter. The transistors in the Procon can't operate 48-volt relays in the number 5 crossbar, and the crossbar logic levels would just fry anything on the Procon. So the scanner distributor provides the Procon with a bunch of reasonable TTL logic level inputs and a bunch of relays to send output signals back into the 5XB. Unfortunately for us, our Procon was dead, and we can't find any board-level schematics of it. We have higher-level schematics of the circuit as a whole, but when it gets down to the individual components, they just show us logical blocks instead of the components themselves. Also, the Procon doesn't use regular 7400 series logic like you might expect from a computer of this era. It uses mostly custom Western Electric ICs, many of which we have almost no data on. Any data that you do find online probably came from us. Now, we could reverse engineer the entire Procon, but that was not really the goal here. We just want to get diagnostic data out of the number 5 crossbar and not have to worry about running out of blank trouble cards. So, instead of trying to revive the Procon, we thought that we could build something better. And we did. This project actually started about 6 years ago. Museum volunteer Astrid got an ESP32 and wrote a basic working state machine in Lua in a couple of days. Why Lua? Probably because Astrid was writing C professionally for her day job and wanted to try something different. You don't want your hobby to feel like work. Anyway, once she was satisfied that she had some bare bones working code, she wired up the ESP32 to the scanner distributor and then wired up the scanner distributor into the trouble recorder circuit. That part actually took several weeks, since this bit of the machine is maddeningly complex, even for experts. But eventually she got through it, and we started to see some signs of life from the new thing. The ESP32 gathered the trouble record data and then submitted it in an HTTP post to a server that we have on site here. The server-side Python code took the data and transformed it into a JPEG image of a trouble card with holes punched in it. The code worked, but there were several bugs to squash. The most troublesome one was random vertical columns of punches down the card. Now, this would happen if a scanning lead was falsely grounded. Each time it goes to punch a row of holes, if one particular lead is always grounded, that hole in the same horizontal position would be punched in each row in our digital card. But for the life of us, we couldn't find a false ground anywhere. And what's weirder is this artifact didn't appear on real trouble cards, only on the ones we captured with our ESP32. That seemed to indicate that we had a wiring issue in our part of the circuit, but each time we tested, the weird vertical line moved around. Sometimes it wasn't there at all. Sometimes it went away for a while and then came back randomly. It was truly a Heisenbug, and it was one of the most annoying things to troubleshoot. Astrid's code was sensible, so we started to think that maybe the cards in the scanner distributor had gone flaky, and maybe there was a bad IC or something. Seeing no other options, we started swapping them out with spares, but to no avail. It seemed that no matter what we did, we still had the random vertical line problem. To make matters worse, when I was troubleshooting alone one day, I accidentally shorted the ESP32 to frame ground, and because of the way its power supply worked, frame ground was about 45 volts above the ESP's hot rail. So that did an excellent job of frying the whole thing. Peter was able to replace the ICs in the scanner distributor that took a hit, but Astrid had perhaps somewhat optimistically soldered the ESP32 into place, and I got frustrated with the whole project and let it sit for several years while I moved on to other things. Fast forward to March 2025 when I decided to pick it up again. I got a new ESP32, wired it up using this nice breakout board, and then I reviewed the Lua and Python code and fixed some bugs that I found. Nothing major, but trouble cards were coming out mostly consistently at the right time and with almost all of the right holes punched. But there was still that pesky vertical line thing that I was unable to fix. This is when museum volunteer Max got curious about how the thing worked and entered into the picture. He spent some time verifying that the scanner distributor was really working as designed, and then he started dissecting the code. Max began to suspect that there was a timing issue internal to the ESP32 that was causing the strange line of dots to be printed on the card. But much to his annoyance, he couldn't find good documentation on how Lua is implemented on the ESP32, and in particular, he couldn't find any documentation that would let him explore possible timing inconsistencies on the chip. For all he knew, some Wi-Fi polling or other job could be interrupting the execution of our scanning code, but without deep-level hardware insight into the firmware of the thing, there was just no easy way to tell. After spinning on this for a few weeks, Max decided to just rewrite the code in C++ using the Arduino framework. This was basically a straight port. All of the logic, function names, and everything else about the code was just brought directly into C++. Much to our amazement, the new code worked perfectly. No more vertical lines. As part of the process, we also took oscilloscope traces of the various leads coming out of the ESP. I didn't save those traces, but we were able to confirm that with the old code, at random intervals, every few seconds, one of the pins was being driven high for a few milliseconds. We never did figure out what specifically caused that, but the fact that it didn't happen on the C++ implementation told us that Lua just wasn't a great choice for writing timing-critical real-time code. The Procon simulator code is pretty straightforward, but I'll quickly explain what it does for the curious. Normally, the thing is idle and is waiting for a signal from the number 5 crossbar that the machine is requesting the use of the trouble recorder. The number 5 does this by asserting a lead high, which is picked up by the scanner distributor and then sent to our ESP32. Once our code recognizes the request, we enter into one of several scanning states. Here, we operate each of the scanning relays in order from the highest numbered to the lowest, and we read out the data from those relays into our buffer. Each time a scanning relay operates, we have to wait 32 milliseconds for contact to bounce, and that wait period is the primary way we set timing for the whole show. Once all 9 sets of scanning relays have operated and released, we now have a full chunk of trouble record data from the number 5, and we can enter into our transmit state where we post the data as a blob of Boolean values over to our server for processing. Regardless of whether or not the transmission was successful, we need to make sure to release the markers in the number 5 and allow them to resume normal call processing, since one or more of them were halted for the duration of this trouble record. On the server side, things get a little more fancy. I started out using the JPEG card image, but after talking with other volunteers, it became clear to me that there was a better and more efficient way of doing this. If we had the Boolean holes data that we use to generate a JPEG, why didn't we actually just take the time to structure that data into something useful and perform some analysis on each card? While we were at it, we could probably just render the card in real time in the browser instead of creating a brand new static image each time a card was processed. Browsers, after all, are very good at things like this. So I started picking apart the server-side code and turning it into a full card processing engine instead of an image creator. The server-side code has to know the layout of the card and then transmogrify the data it gets into something that is recognizable. Astrid had started this process, but I took it a step further. I created a list of each position on the card and mapped the incoming data onto that list. I then wrote some helper functions to query punch data by name or by position on the card. With these abstractions, we can now ask the software something like, "Is this hole punched?" and get a reasonable response back. The next task took me a couple weeks of work. I had to go from reading individual punches to analyzing particular groups of punches. In order to do this, one has to know how the number 5 crossbar works and how the data on the card is actually structured. It's not simply read in a linear fashion. Some punches change the meaning of other punches, and depending on what type of call the machine was handling, the list of expected punches can vary dramatically. How do I take all of the knowledge in my head about how the 5 crossbar and these cards work and convert it into code that is both readable and sane? There is a totally naive approach to this where you could just follow a flowchart, but that has its shortcomings. The more I explored the flowchart idea, the more I kept running into walls or coding myself into corners. But on the other hand, I couldn't just YOLO it and analyze the card in whatever random order I felt like. At the same time, I wanted to separate out the data gathering stage from the actual analysis stage. This was complicated by what I said before, that depending on the particulars of what the card was reporting, some data could be invalidated by holes punched elsewhere, or some data would have to be treated differently depending on other factors and so on. I eventually settled on a way to do this. I created a dictionary of the card and sorted the punches into logical groups. Phone number goes here, marker status goes here, cross detection goes here, and so on. This was closer to how a human would think about the card. I could then analyze groups of punches and record the result of that analysis. This allowed me to approach decisions about the data in a more manageable way. I decided that custom exceptions would be a good way to communicate errors that were detected in the analysis. These exceptions are each handled, and the state that generated them is recorded before allowing analysis to continue. As analysis progressed further, we could encounter more errors, which would continue to accumulate as part of the final output. Once I had these exceptions associated with their logical groups on the card, I can then arrange them by order of precedence and assign the card to a bin. A bin, in this case, is just a way to sort cards into batches of similar failures, which makes meta-analysis possible. The whole idea of binning in this context came from what the original ATA software running on the PDP-11 was doing, and the PDP-11 version of it came from this thing here. This is where original paper trouble cards were sorted by type. When a stack got pretty tall, you knew that you had a particular problem that was happening more often than others, and it warranted deeper investigation. Finally, I wanted to present a nice UI for the whole thing. I'm someone who appreciates a well-designed tool. And since I was going to be the primary user of this, I wanted to design something that worked really well for my brain. It's still a work in progress, but I'm very happy with how far it's come. On the main page, the card itself is front and center. Even after all this analysis, I still wanted to present the trouble card as the primary interface between me and the telefilm switch. To me, the card is a faithful and useful representation of the machine's feelings. The card layer is a static JPEG, and the holes are rendered by the browser from the card metadata. This was actually suggested to me by volunteer Matt, and he was so right about this. It's much, much faster than what we were doing before. The application has two main views. The first one is meant to simulate the output tray of the actual trouble recorder. It auto-reloads the image to always display the most recent card. The shiny green dot in the upper right reassures you that there is an event listener open to the server, so you are seeing the most recent data. If the dot turns red, that means you've lost connection to the server, and whatever data you are seeing is probably stale. Next to that is a manual reload button, because I don't trust computers, and I always keep a hammer under my desk, just in case. On the far left is a drop-down that allows you to look at previous cards. These are all time-stamped, and the action is similar to thumbing through a stack of cards while it's still in the output tray. Then there's these two links here, card bins and settings. Let's look at the bins page first. This page is meant to allow for a deeper analysis of patterns that occur over hours or days. The drop-down lets you select the time frame that you're interested in, and when you do so, it displays a list of cards from that time period sorted into their bins. As you might expect, if you click on a card, it's displayed, and below the card is the metadata that was captured during the card analysis stage. There are also helpful human-readable error messages that can point you in the right direction for troubleshooting. The metadata is also available as an unformatted JSON blob by navigating to cardmeta/cardname. This can theoretically be used by another program to gather the card data and present it in a new way outside of this application. The URL of the card display page also serves as a permalink to this particular card. So if you need to share it with other folks, you could just throw this URL into a chat or whatever, and this card will always appear like this in the browser, just as long as the JSON still exists on disk. I should probably come up with a better storage system for that than just throwing it all into /temp. Back on the main page, our final stop is the settings link. There's only 3 settings for right now. The first one toggles auto refresh on and off. That way, if you're looking at a card on the main page and you don't want it to disappear when a new card comes in, you can just turn that off. The second and third settings are really cool, though. Let's turn them both on. Okay, now the metadata is displayed on the main page, so we can scroll down and read that here if we want to. And what's really neat is that now when you mouse over punches on the card, tooltips show you what each punch means. And I know what you're thinking. Did Sarah really write out descriptions for all of 1,080 of these punches? The answer is yes. Yes, I did. They do exist in paper form, but OCR isn't perfect, and it was actually easier for me to just type out the description of a punch that was actually helpful instead of manually correcting all of the terrible OCR for this 50-year-old document. An unintended byproduct of this is that it helped reinforce the punch meanings in my mind, and it encouraged me to dig further into each punch meaning as part of my research for completing this feature. All in all, I'm really happy with how this turned out. It involved many volunteers over several years, and now troubleshooting the 5XB is easier, faster, and more environmentally friendly. And I don't have to be so stingy with our remaining stock of trouble cards. In addition to helping me work on the number 5, I hope that this interface can someday also help newbie volunteers who might be a little daunted by the machine. And since the card data can be accessed as JSON, it's possible to plot graphs or present the data in totally different ways that I had never thought of. If you've made it this far, you might be wondering if this is available publicly. Not yet, because it's running on a little potato of a server, and I'm reluctant to put the URL out on YouTube for the entire internet to hammer. And I really do not want to get into web server maintenance as a hobby. So I'm being a little cautious. But maybe some other day, some other volunteers will want to take that on. I got to get back to work on the other projects that are happening, and I will surely do a video about those soon. So if you've made it this far, thanks for watching to the end, and I'll see you soon. Bye.